Hi everyone, this video is about the Wilcoxon signed rank test, and I will talk briefly about when you can use it, and then I will give you an example. So the first thing to know about when you should use the Wilcoxon signed rank test is it's got to be used for numeric data. And not only should the data be numeric, but it's going to be set up as two samples, and the two samples should have paired observations, meaning for every observation in the first sample, there's one that's paired with it in the second sample, and that pairing could be in the form of, say, siblings. You have a random sample for the first sample, but then every observation in the second sample is a sibling of someone in the first sample. That makes it paired. Maybe you have multiple observations, so you have a drug that you give and you take one measurement on a sample of people before you give them the drug, and then you take another measurement on the same exact people after you give them a drug. So there you have paired data too, because every person appears both in that first sample and in the second sample. So you're going to want to use it for paired data. And then finally, this is a non-parametric test, meaning it's not relying on the shape of any underlying distribution. We're not requiring that the data itself have a normal distribution or any distribution. The only thing that we require for the underlying data is that the differences in each pair, which is really what we're looking at the difference between every pair of observation. Those differences should be symmetric. And all that I mean by that is the underlying distribution that they come from should look the same as you go out from the middle to the right and the left. That's all I mean. So if that condition is satisfied, then you can use this test. The other option when we have numeric data in this paired structure that does not meet the any kind of distributional assumptions, we can also use the sign test. The sign test doesn't depend on the data being normal or anything like that. And in fact, the sign test doesn't even require that the data be symmetric. So you can use that test. It's not as powerful as this Wilcoxon signed rank test, which we're talking about right now. So let's take a look at the example problem. It says there are 9 horses and a veterinary anatomist is measuring the density of nerve cells at specified sites in the intestines. And they're giving the results for site 1 and site 2 for each horse, which we're going to see in the table on the next slide. And they do mention that each density value is the average of counts of nerve cells in 5 equal sections of tissue. So they are at each site measuring these counts of nerve cells in 5 different sections of tissue, but then they're averaging them, and that counts as the result for site 1 or site 2. So even though they're taking a bunch of different measurements per horse, you're going to end up with 2 numbers that you're looking at, the average for site 1 and the average for site 2 in each horse. And here's something that I think it's important for us to look at, and that is the null hypothesis of interest, is that in the population of all horses, there is no difference between the 2 sites. That's how your book talks about the null hypothesis for a non-parametric test like this one. And I just want to emphasize that that's different from how we talk about the null hypothesis in the paired t-test, for example, where we really are talking about the population mean of the first group and of the second group and saying, are they equal to each other? Is the difference between them 0? Or making other statements about the population means. Here, we're not talking about the population means. We're talking about the distributions generally. Are they the same or are they different at these 2 different sites in the overall population of horses? So here's our data. We can see, first of all, that we've got n equal 9. There are 9 animals, and each one has this measurement taken at site 1 and site 2. So that's what makes it paired data, just as a reminder. And so here's the approach we're going to take. The first thing to do is I'm just going to add on some additional columns here. So the first new column is going to be just the differences. So that's what we're always doing when we have paired data, is we're starting by looking at the differences for each row in the table. We're looking at the difference between the two groups. So in this case, site 1 and site 2. And that's going to be what we actually work with, are those differences. So you can see for the first animal, we're looking at 50.6 minus 38.0. And that's going to be 12.6. And I'm going to go ahead down the rows here and just get the difference for all of the pairs. So this one is 20.6, this is 12.0, this one is minus 2.0, because remember I'm subtracting from right to left here, so minus 2.0, 4.6, minus 2.2, 9.8, minus 0.2, and 10.8. The next thing we're going to do is look at the absolute value of the differences. That's also pretty easy. 12.6, we're just looking at the positive values for each of these differences. Okay, so once we have the kind of unsigned differences, the absolute value of those differences, then our next step is to rank those values. So I'm going to start with the smallest one and work my way up. So the smallest one of this row of the absolute value of the differences is here. The 0.2 has rank 1. And then we find the next largest. It looks like it is here. And the next largest is the 2.2, so that's rank 3. And we just keep working our way up. Let's see, I guess the next one is here at 4.6. And then here, 7, 8, 9. So there's my ranks 1 through 9. Now the last column I'm going to make here is the column for the signed rank. Meaning, I'm just going to take those same ranks I already have, and then I'm reinstituting these signs here. So the minus signs that are along here, I'm going to take those and just put them on my ranks. So 8, 9, and 7 are the same, but then the rank of 2 is going to get a minus in front of it. And then I have a 4, and then minus 3, 5, minus 1, and 6. Now we will actually formulate the test statistic here, and that is W plus is just the sum of all the positive ranks. So the positive ranks are the ones that 8 plus 9 plus 7 plus 4 plus 5 plus 6. So when I add those guys up, I get 39, and then W minus is going to be the remaining ones, the negative signs. And I'm just going to give the sum of those values. We've got -2, -3, and -1, but I'm not making it negative. I'm just adding up the positive versions of those ranks, so I get 6. So now the test statistic is going to be the maximum of W plus and W minus. So that's clearly just 39. And that's what we're going to take to the table. So I'll just put that here. Go to table for the Wilcoxon signed rank test. But to do that, we're going to need to know what row to look things up on. And the relevant piece for that is the fact that we have 9 pairs. So our n equals 9. And we can look up on the table what the p-value is for a test statistic of 39 for n equals 9. So let's look at the table. Remember, our test statistic was 39, and our number of pairs was 9. So that means we're going to be looking along this row here. There's the 9 for the 9 pairs. and we look at these guys right here. And what we're looking up is test statistic 39. That's going to be these bold numbers here. So we're trying to find where 39 would be in this table. It's going to be somewhere in these two cells here because I've got the 37 and I've got the 40. So 39 is in between there. And then these numbers here in italics are the corresponding p-values. So we can say that our p-value is, since our test statistic is 39, our p-value is between 0.039 and 0.098. Now, if we had our usual alpha equals 0.05, then this doesn't really help us because we can't tell if the p-value is larger than 0.05 or less than 0.05. We just know it's in this range. And that's because we're using this table as opposed to computer software to give us the p-value. If we used computer software to get the p-value, then we would just get the exact p-value corresponding to our test statistic of 39. But as it is, we can just get a range using the table. So for alpha equals 0.05, we can't even make a decision to accept or reject. But for alpha equals 0.10, if we decide to make that the significance level of our test, then we can say that for that level of alpha, that yes, we reject the null hypothesis. We say there is a difference in the two sites for this measurement in the horse population. Now, just as a little extra addendum here, I wanted to mention to you guys what you do in a situation where you have ties in the differences, because a few people have asked me about this. So what I've done is, you can see I have changed a couple of the values here to make it so that we actually end up with some ties when we do the differences. So I've left almost all the differences here because they stayed the same. I didn't change their original data, but I did for rows for animals 5 and 6. So you can see that both of them are going to have, for their difference, minus 2.0, minus 2.0. So then when we go to do the absolute value of the differences, it's 2.0, 2.0. So now we have to think about how we're going to rank these. So as before, rank 1 goes to this one here, animal number 8, because it has the smallest number for the difference. But now you can see I've got 3 differences that are the same. So here, here, here. They're all 2.0. And so how do I deal with that? I think the easiest way to do this is going to be to just go ahead and rank them. So they're tied. They're going to take up the next 3 ranks. So 2, 3, and 4. They're all the same, but I'm just going to give them the next 3 ranks for now and then finish out my ranking, and I'll come back to them. So ranks 2, 3, and 4, and then this one would be rank 5. This is all the same as before. 6, 7, 8, 9. So I would go ahead and just finish the ranking, but then you've got to come back and recognize that since these guys all have the same difference, then they should also all have the same rank. So what we need to think about is what the mean of these 3 ranks is. And the mean of those 3 ranks is going to be 2 plus 3 plus 4 divided by 3, which is just 3. So I'll erase them all and give them all the same rank of their average rank, which is 3. And if you do it that way, then you can go ahead and continue the rest of the problem in the way that we did before, just using these averages for your ranks for the tied differences. That's it. Thanks, guys.